right, so we're in section 1.5, the last little bit we're doing in chapter 1, just a couple seconds. Inverse functions. So before we get into the math, let's talk for a second. What do we mean when we talk about an inverse? What are we doing? What are we saying when we're saying we're looking for an inverse? What do we mean? Opposite. So it's kind of the opposite. What? Oh, okay. What things do we do regularly that are opposites in math? Perpendiculars, they're opposites, definitely opposites in a way. So that, and we'll kind of get to that a little bit when we're talking today. Mm-hmm. Addition of subtractions, I think someone up here said that as well. Flipping the x and y axis, okay. Yeah, so that we'll talk more about that as well. Mm-hmm. Okay, so we're talking, we use addition and subtraction are opposites of each other. So addition is the inverse of subtraction, is definitely a way we can think of it, or multiply, divide. And when we're solving equations, when we multiply or divide, add, subtract, what are we saying that one is doing to the other? Canceling it, or so cancel is good. It's another word we use a lot. Reciprocal? Okay, so that would be multiplication, division. So I'm thinking of, if we say, I tell my students a lot of times when they're just learning solving equations, what undoes something. So addition undoes subtraction. Multiplication undoes division, and vice versa. So inverse functions, when we're talking about functions, inverse functions undo each other. So we're talking about undoing something. So that's our kind of our bottom line idea. So we use there's one particular pair of inverse functions that we use quite a bit. Other than adding, subtracting, multiplying, dividing, there's one that we use. Factoring. So factoring is kind of undoing the multiplication, undoing the putting together. In terms of functions, what function can anybody think of what pair of functions we use quite a bit when we're solving equations? So what about if we had something like that? How would we solve that? Squared. So squaring undoes square root. So square and square root are inverse functions. That's probably the most common pair that we've worked with so far, other than adding, subtracting, multiplying, and dividing. Is squaring undoes square root undoes squaring. So that's the most common one we've worked with, and we've done any of the power functions and the root functions. We've used those. Cubing undoes cube root, etc. So the basic idea of an inverse function is that it undoes another function. Now if we have a table of values, and a couple people mentioned it when we were talking talking about inverses. If we have a function that's defined by a table of values, or if we have a table of values for a function, what happens, what does the inverse function look like with the table of values? What does it do to the table of values? So if we have our x, our t chart, and y, we have our x's and y's listed out. How do we find the inverse function from a table of values? Someone said it before. I don't think we were necessarily thinking of table of values, but we definitely said it. Not quite the reciprocal, but what did you say? Someone said flip it. So the x's and the y's get switched. So if we're talking about inverse functions, if we're looking at a table of values, the inverse function would switch the x's and y's. So if we think of x squared and square root of x, if we think of those two, one squares, the other, one is a list of squares, the other is a list of the square roots. So we're switching the x's and y's. So if we have inverse functions, we have table of values for inverse functions, the x's and y's get switched. They switch places for the inverse functions. And someone definitely mentioned this one. If we're looking at graphs of inverse function, if we have a function and its inverse graphed together, what happens with the graphs? Remember? If we switch the x's and y's, what does that do to the graph of your function? Switches the x's and y's. So, what does that do to the graph? It has to do with perpendicular. Reflects over y equals x. So the graphs of inverse functions reflect over the line y equals x. So that has to do with that idea of perpendicular, because if we draw a line from the function to its inverse, it's perpendicular to the line y equals x. So let me draw an example of this reflection, just so we can visualize it. So for table of values, we're switching the x's and y's. For graphs, we're flipping over the line y equals x. So for example, if we had, there are my axes, I'll draw the line y equals x in red. I know this isn't perfect, but you get the idea. If this is my function, this would be the inverse. So this is what we mean by the function reflecting over the line y equals x. Line y equals x is a mirror, and if I connected this point with its reflection, it would be perpendicular to the line y equals x. And anything that was an x value on this function would be a y value on the inverse. So that's what we mean by the function inverse. Reflect. So if we have a function written down, f of x equals something, we need a way of knowing. We don't want to have to graph everything or look at a table of values to decide if it's if two functions are inverses of each other. So there's a way that we can figure out if functions are inverses of each other. So let's write down this definition. How do we know if two functions are inverses of each other? So we have functions f and g. And these functions are inverses of each other. If and only if we have two conditions. The composition of f with g equals x. So we make the composition of f and g and we get x back out. And this is for x in the domain of g. So we have to be able to, it's something that we can be, that's in the domain of g. And g of f of x, the composition going the other direction gives us x also. And for this one, we have to have x in the domain of f. So this is how we test two functions to decide if they are inverses. One undoes the other. We plug in x, we do the composition with the inverse, and we get x back out. We end up not doing anything. So this is our test for inverses. So we form the composition going both ways, and we get x back out. Plug x in, do everything, we get x back out. One undoes the other. So this is our test for composition. So if you're going to have problems tonight in the homework that say, determine if these two functions are inverses of each other. And this is your test. Form the composition, see if you get x back out. Questions on that? All right, so we know how to decide, we know what happens when functions are inverses of each other. We switch the x's and y's in the table of values. They reflect, the graphs reflect over the line y equals x. They undo each other. We decide how to determine if we have two functions, how to decide if they're inverses of each other. We remember how we tell from a graph how to decide if a function has an inverse. Hi, Ms. Fox.
Sir, please? Yeah.
Oh, yes.
Did you copy them already or not?
I did not.
Sorry, guys.
All right, let's go back even a little further. How do we decide if, from a graph, if the graph represents a function? We have a nice little test, yes. Vertical line test. The vertical line test tells us if a graph is a function. So we had a graph of a circle. It fails the vertical line test, so a circle is not a function. So if we're looking at a graph, how do we tell if that function has an inverse? What's our test then? If we tell if it's a function, if it's a vertical line test. Right. Okay. Perfect. So going from there, what is our test? Hopefully this rings a bell. What is our test for an inverse then? Okay, if it's mirrored, we want something easy that we can do without a lot of work. What do you think, Alana? Horizontal line test. Very nice. So we tell if a function has an inverse by the horizontal line test. So from a graph, we can tell if the function has an inverse. So let's draw a couple of quick pictures here. So if I have a graph, a parabola. So y equals x squared. Here's my horizontal line. And this would be a fail because it crosses the graph in two places. So this function does not have an inverse. If we look at a cubic function, my horizontal line here, no matter where I put it, it's just going to touch the graph in one place. So this would be a pass. And this function does have an inverse. So a horizontal line test from a graph, that's what tells us if our function is going to have an inverse. Now something special happens when a function does have an inverse. We call that function one-to-one. So we call that function one-to-one. And what that tells us is if a function has an inverse, it is one-to-one. If it is one-to-one, then it has an inverse. What one-to-one means is for each x value, so each value in the domain, there is exactly one value in the range. One y value. So that's the range. So if we were looking at a table of values, we have no repeats in the x's or y's. For each x, there's exactly one y. So that's what happens when we have a one-to-one function. A one-to-one function has an inverse. If the function is one-to-one, then it has an inverse. So that's an important property of functions with inverses, is they are one-to-one. Each x value gives us exactly one y value. And this also means when a function is one-to-one, that the inverse, if a function has an inverse, the inverse will be a function. So if we have exactly one y value for each x value, if I'm looking at my table of values, there's going to be, if I flip it around, they're going to match up exactly no matter which order I put them in. So a function with an inverse means that the inverse is also a function. If a function has an inverse, the inverse is also a function. We can tell by the horizontal line test, or we can form the composition and see if we get x back out. So questions? Questions so far? Just talking about what functions, what inverses tell us, how we tell if we have an inverse. Now the other task that we might have to do, or that we will have to do, is finding inverses. If we're given a function, how we find its inverse. And I know that we've done this before. If we're given a function we have a few steps that a nice little procedure that we use to find the inverse. Does anybody remember it? Yes.
The x with the y.
Okay. Switch x and y. And then we do what? Solve for y. That's how we find our inverse. So we're switching the x's and y's. That's what inverse functions do, switch x's and y's, and then we're just rearranging the equation so we see that we get the equation working in the other direction. And then at the end we have to make sure whatever we end up with, write y as f inverse. And I forgot to write that we call this notation when we have an inverse function. You might want to go back and add it here. Here. We say that g of x equals f inverse of x. The little -1 means inverse. And it's important to remember that f inverse is not the same as 1 over f. We don't just make the reciprocal. So this -1 notation tells us we're talking about an inverse function. All right, so what I want to do is just a couple of examples of finding an inverse function using these steps. So questions before we go on. Basic idea, inverse functions undo each other. When we graph inverse functions, when we graph a function, it has an inverse if it passes the horizontal line test. The inverse functions switch x's and y's in the table of values. The graph reflects over the line y equals x. So those are the main things. Now we want to talk about how we find them. So let's say that f is the square root of, the cube root of x minus 5. And we want to find the inverse. So the first thing that I'm going to do, I don't have a y here. You can always write f of x as y equals. Instead of using function notation. Now I'm going to switch the x's and y's. Everywhere I see an x, I'm going to put a y. Everywhere I see a y, I'm going to put an x. So I'm going to do that part in red. X equals the cube root of y minus 5. So I'm switching the x's and y's. Now I'm going to solve for y. So how do I solve this for y? Cube both sides. So I get x cubed equals y minus 5. Subtract -5. So add 5. So I turn it around. Y equals x cubed plus 5. And I'm just going to rewrite this. F inverse of x equals x cubed plus 5. So this is f inverse. And to verify, if I wanted to verify that I came up with the correct answer, what would I do? How do we verify that functions are inverses of each other? We could graph it. What's that? Okay, put a number in x and see if it's a y. Now if we use numbers, the hard thing about numbers is it might work for one number but not others. How do we guarantee that it's always going to work? What's our test? Plug the inverse, so form the composition. And what should I get back out? X. I should get x back out. And it has to work both ways. I have to be able to form the composition of f with its inverse and the inverse with f. So I have to do the composition both ways, and I would get x back out to verify that I came up with the inverse. So to verify, if the problem asks you to verify that these two functions are inverses of each other, algebraically, you form the composition in both ways, f of g and g of f, and you should get x back out. All right, let's look at one more. That's a little trickier. This type gives people trouble sometimes. So here I have f of x equals x minus 4 over x plus 2. Now what I don't want you to do, I see this every year, I get f minus 1 of x equals x plus 4 over x minus 2. I can't just switch the signs. And I can't say that this equals x plus 2 over x minus 4. I can't just flip the fraction. So I'm going to write y equals x minus 4 over x plus 2. Switch the x's and y's. So I have to switch every x and every y. So I get x equals y minus 4 over x plus 2. Sorry, y. Just broke my own rule. Y plus 2. Now, how am I going to go about solving this? What do I have to do? Multiply both sides by y plus 2. I'm going to do that in red. Now I'm going to distribute here. xy plus 2x. I'm multiplying. These cancel. Equals y minus 4. Now this is where people start getting confused. What do I need to do here to get to solve for y? What's going to be my next step? What's that? Add 4. Okay, I can add 4. My problem is I have this xy thing here. What can I do with that? Okay, so our first step is going to be, I have two terms with y's in them. Let's get all of those terms together. So now I'm going to subtract xy from both sides. So 2x plus 4 equals y minus xy. So I have all the terms that have y in them together on one side of the equation. And then, like I said, let's factor out the y. 2x plus 4 equals y times 1 minus x. Now we're home free, right? I can just divide both sides by 1 minus x. So y equals 2x plus 4 over 1 minus x. And then I'm going to rewrite that. F inverse of x, 2x plus 4 over 1 minus x. So problems like that are a little trickier. Yes?
Can you illustrate how negative xy becomes 1 minus?
I factored, so each of these terms has y in common. So I factored that out. So just like if I had 2 minus 2x, I can write this as 2 times 1 minus x. 2, the y takes the place of the 2. Same idea. Questions on that example? All right, so finding inverses, switch x and y, solve for y. Verifying inverses, form the composition. See if you get x back out. Reflect the graphs over the line y equals x. Table of values, switch. Those are kind of the big picture things about inverses. Okay, homework, and then I have something to show you. EOO, every other odd. All right, there you go.